In nature, quantities tend to change accordingly to an exponential growth function, well, exponential growth and decay function. And the function is now the reason why nature tends to change exponentially growing and or decaying in this function is because quantities in nature tend to change slowly, smoothly, and continuously. Whenever they start changing, there's no going back unless an external forces intervene. But naturally, quantities change using this exponential equation. Now let me break it down. What PO means, P with the base of O, is the initial quantity. Initial quantity. That is the quantity that you start with before the change, or before the change, before the growth, or before the decay. E, as you might remember from our last class, is that E is used by a scientific consensus to explain exponential growth, which is basically the number 2.718 ... because it stretches to infinity. K here is the rate at which the growth or the decay happens. So this is the growth function, and the decay is exactly the same function, just with a negative sign. So the rate of change. And T is the time that you're trying to figure out, or that you already have. It depends. You're trying to measure the change, the continuous change, whether growth or decay, within a certain period of time. When in those cases the T will be given already, or you're trying to figure out the time, which will be the exponential, the unknown exponential you're trying to figure out. Time of change. Now like I said, we might have the time or we might not. So basically we can solve for any of these variables that we want, depending on the ones that we do not possess currently. Those are the ones that we're trying to look for, right? So let's give an example. The population of Kenya, this African country, this beautiful African country. What does this mean? This is the population of Kenya, this African beautiful country, in 25 years. So why? How does this mean? So the population of Kenya from, let's say, 2004 to 2029. In 2029, the population of Kenya has grown to 3.9 million. In 2004, it has grown. It was the initial quantity. It was 1.9 million. Between this time is 25 years. So between 2004 and 2029 is 25 years. We're trying to find at what rate does the population, the initial population, 1.9 million, grew to 3.9 million between that period of 25 years. So how will we do it? The way we will do it is we will solve this equation using natural logarithms, because as you might remember, natural logarithms are used to solve for unknown exponentials. Now let me break it down. What I did here was I solved for the unknown exponential by first dividing by initial quantity to the other quantity, then by using natural logarithms to be able to access this unknown variable, leading to k multiplied by 25 equals natural logarithm of 3.9 over 1.9. Now here, remember that the natural logarithm of e to the power of x equals x, which in this case x is k multiplied by 25. Now in order to isolate k, we need to divide by 25, which is exactly what I did here. The natural logarithm of 3.9 over 1.9 over 25 equals k. Now k equals 0.028. What does that mean? That means that the rate, if we multiply this number by 100 to get the percentage, the rate at which the population of Kenya grew from 1.9 million to 3.5 million, sorry, from 1.9 million to 3.9 million in 25 years was 2.8%. Now there are 4 properties to this function that you might have if you want to optimize stuff rapidly. Those 4 properties are: the first one, double time. Now double time is the time required for the initial property, for the initial quantity to double. How do you attain this? By using this formula: double time equals 2p0 EKT. Now if you multiply the initial given quantity by 2, that's what you're trying to attain, right? So this is the formula used for when you want to figure out the time it takes for the initial quantity to double. Now the second property is half-life, which, as you might know, given the game of words, half-life is the time required for the initial property to cut in half, to be cut in half. That is the initial quantity over 2 equals our growth decay function. Now half-life is the time required for the initial quantity to be cut in half, which might be important in any aspect of life to have. You sometimes want to know the quantities when it's gonna be half or when it's gonna double, because you're trying to project things. The third and fourth property for our growth and decay formula are very similar to each other. The first one, number 3, is the compounded interest formula. Compounded interest, which, as you might know, is widely used in the realms, or basically anywhere where you are dealing with money, management, and time, which, I mean, every single company deals with that. The compounded interest property states that a quantity will be equal to initial quantity multiplied by 1 plus the rate at which that quantity, that interest, increases or decreases to the power of t. So this quantity, remember the last class that I was saying that the continuous growth rate is more accurate than the regular growth rate? Well, this will be the growth rate but now in terms of finance and economics, which it's called the compounded interests. The fourth property is the continuous compounded interest, which, as you might know, since it's more accurate and continuous, equals our initial exponential growth and decay formula. Now, in order to break property number 3 and 4 in terms of economics, finance, and management, you have to think about the compounded interest as the formula at which the interest is added to the initial quantity once or twice per year. So you only have a couple of times to add the interest to the initial quantity. However, the continuous compounded interest formula is when you're adding the interest at any given time possible and any possible instance that you can. So let's say you want to pay your credit card once a year, that will be the compounded interest. But if you want to pay your credit card once every week, that will be the continuous compounded interest, since you are trying to pay the card and you're trying to accumulate the interest as most as possible, as available as possible. Now let's do an example about this compounded interest and continuous compounded interest. Imagine there is a bank, Chase Bank. Well, let's not use names so they don't sue me. But let's imagine a bank, right? Your own bank. So let's say you have your own bank that has an 8% interest. If you deposit $5,000 right now, how much money will you have in 3 years? Let's do that. Using the compounded interest, you have the initial quantity, $5,000. The interest rate is 8%. That's what we said, right? Therefore, 1 plus R, which is the rate, 8%. 8% in terms of a decimal is 0.08 to the power of t. Now, using the continuous compounded interest, you have the 5,000 as well. Have e to the power of the rate, which is in terms of decimals 0.08 to the power of t. Now, remember how I said that it was in 3 years? T equals to 3. T equals to 3 years. You want to project how much money you're gonna have in this bank in 3 years if you deposit today $5,000 using two methods, the compounded interest and the continuous compounded interest, which basically they differentiate between each other by terms of rate, by terms of how often you pay the interest, or the interest gets paid to you or to your account or to your quantities or to your stockpile, whatever the scenario is, using this formula. Now let's solve this. Now, using this, the compounded interest and the continuous compounded interest, we find that using the continuous compounded interest formula, we get more money, about $58 more. Of course, sometimes there are people that it's a difference, and for other people it's not. But we find out here that one, the continuous compounded interest gives us more money. Why? Because we pay we pay the debt, or in this case, an interest gets paid to us at any given available instance. You know, we get that money anytime we can. They give us that money anytime we can. Whereas in the compounded interest, we get that money on a discrete amount of times, let's say twice a year. Therefore, ending up with less money in 3 years with the compounded interest formula than with the continuous compounded interest formula. Now, this gets more interesting by the minute, or by the second perhaps, using continuous growth rate. If you catch the joke, then that's good. But using these formulas here, we can project what a future value is gonna be, or we can retrospectively see what a present value was at a point at the past. So let me explain here. Here B equals or future value. P equals or present value. Now, how can we project, or can we retrospectively see the value of a future value or a present value? Using these formulas. The future value equals the compounded interest, or vice versa, the present value at a point in the past equals B, the future value, at a given, which in this case the future value will be the present value at that present over the compounded interest. The same goes for the continuous compounded interest. Now, these formulas are used to, like I said, to project and to go back at the past and see what values were, or what values are gonna be in the future or past. Now, here's an example, a very interesting one. Imagine you're on a bed, right? And the artifact that they are bidding, it's a paint by Johannes Vermeer, the Dutch painter. who painted very beautiful paintings. Now they are bidding this this painting, and they claim that it was painted by Johannes Vermeers. However, they give two important variables that you catch, but not everyone does, but you do. That it's carbon 14, which is an important atom used to measure basically the age of any given object, used by geologists, physicists, etc. The current value of C14 of this painting is 99.5%. And we know, because we are a genius and we know our chemistry, we know that the half-life of carbon, of the isotope C14, is 5,730 years. With these two variables, you are able to find basically whether the painting is fake or it is real. So now, how can we solve this inquiry? We know that we have a sense that the painting is fake, but we need to prove it realistically, empirically. And what's best than doing it with math? So how can we start this? Well, we know that we're involving a decay function, a half-life decay function. Why? Because we have the half-life information and we have the rate. So what will be in this case be the function? The function, well, the formula equation is initial quantity over 2, because it's the half-life, or equals to initial quantity multiplied by E to the power of negative K multiplied by T. Excuse me. So we don't know any of these variables except for K. Why K? Because, no, sorry, except for T. Why T? Because T is the half-life. That's the time variable that we have. Therefore, we have this formula now. We only have this variable, but don't worry, we will solve this mystery to determine whether Johannes Vermeer painting is real or not, using math. Here, as you can see, if we divide by the initial quantity, we will remove initial quantity on both sides of the equation, leaving us with 1/2 equals E to the power of K multiplied by 5,730. Now we want to know K, which is the rate at which the painting decayed, which in this case will be carbon 14. So right now it's said that in the present, when we are in this bidding, it's mentioned that its current carbon is 99.5%. We want to know if a painting from this date, 1000, from the 15th century, it's gonna be 99.5%. We are trying to determine that, and to determine that we need to know the rate at which this carbon, specifically this C14 carbon, in this specific case, decayed. This is why we're solving for K. We're trying to we're trying to find the truth using math, which is the best goal in life. Now the second step is I took the natural logarithm in both sides, and as you might know, natural logarithm of E is to the power of x is simple x, which in this case x is minus K multiplied by 5,730, which, using some math, we can get that negative natural logarithm of 1/2 over 5,730 equals, or K. We have K now. Initial quantity, which in this case will be 0.99. Why this number? Because in terms of decimal numbers, 99.5% is 0.995. Or initial quantity. Why our initial quantity? Because this current painting is our quantity. We just don't know what the quantity is, but we have the fact that it contains 99.5% of its carbon, equals the initial quantity, which we don't know, to the power of the decay function. We know that for a fact. Now, in order to solve for this, we need, of course, we would divide the initial quantities that we do not know, both sides, leaving us with this number. Now, in order to solve for the unknown variables, we get the natural logarithm in both sides. Now we know that k equals ln, which is the natural logarithm of 1 over 2 over 5,730. So we plug it in and we divide it to move it to this side to solve for the time, therefore leaving us with t equals to the natural logarithm of 0.995 over natural logarithm of 2 over 5,730. And yes, I made a mistake. It was in fact 2, not 1 over 2. Now we have the time. Now what? Now, using this, we determine that this number equals to approximately 41 years, which, if we are in 2024, we can instantly know that this painting was in fact not painted by Johannes Vermeer. How did we get to that? Using decay, exponential decay function, and using two facts. Our current isotope C14 value and the half-life rate. And that's how we proved that this paint was painted 41 years ago. You see? You see how under control you are with math?